Welcome to Chapter 8, Metamorphic Rocks for Geology at Gilgit Community College. In order to talk about metamorphic rocks, we of course need to start with metamorphism. What is metamorphism? Well, metamorphosis is changing form, changing what you are, right? Oh my gosh, I forgot the word. Caterpillar undergoes metamorphism into a butterfly. Wow, that was a butchering of a sentence there. So metamorphism in geology terms is the transition of one rock into another, usually by temperature and pressure, in a way that is different from the other two rocks we've talked about before, being igneous and metamorphic. You change the mineralogy or chemical composition of the rock, and such that metamorphic rock was something and then it became something else, was a parent and is now a new daughter rock, if you will. The way we describe metamorphic rocks is with a grade or a degree to which the parent rock has changed. You could have a low-grade metamorphic rock, which has low amounts of temperature and pressure involved. High-grade metamorphic rocks, which have a high amount of temperature and pressure involved, or an intermediate grade, which would be between the two. A key point here is that the rocks never melt. You never get temperature and pressure at such a degree to where the rocks melt, because then you have igneous rocks. Here are common examples of what I'm talking about here. Shale to slate is an example of some low-grade metamorphism. Does not take a lot of temperature and pressure to compact shale and heat up shale such that it becomes slate. And again, we can notice in those inserts there, the particles, the sediment involved in shale is sort of every which way. It's layered, but it's not super uniform. And then the chlorite and micrograins compact very much to get slate, which is a key difference. High-grade metamorphism would be something like gneiss. Gneiss comes from a granitoid, a granite rock, and the high amount of temperature and pressure fold and compress and alter that original granite to form the nice folded gneisses that we find in our day-to-day existence here on Earth. Not all gneiss necessarily is folded, but it all kind of is too. Not to that scale always. At 200 degrees Celsius, clay minerals, for example, of a shale, let's say, can alter to mica. But the feldspar and quartz, in this example here, remain stable because feldspar and quartz do not melt, do not alter, they don't melt. Feldspar and quartz do not alter at that amount of temperature. So we can have things like a phyllite up here. Phyllite is a mica-based mineral, but it can have little chunks of, say, feldspars, garnets, quartzes, what have you, in it that haven't changed because you have not got that high enough grade of metamorphism. Here is a very well-known chart explaining this process. Sedimentary rocks are your surface conditions. This is your sediment converts, glues together, lithifies in some way to form sandstone, shales, limestones, what have you. As the temperature increases and the pressure increases, you transition into a barrier separating a sedimentary environment from metamorphic environment. And as you continue increasing, eventually you will hit a point, usually around 700 something degrees Celsius, where the rock stops altering and starts melting. You can get partial melting going on at igneous or a complete melt going down to an igneous environment. This chart signifies all the various things that can happen to a rock. So what drives metamorphism? The most important agent involved is heat. At very high temperatures and pressures, rocks become ductile. They will essentially can deform without breaking. Think of rubber, for example, right? You can bend rubber and it won't shatter, as opposed to something hard, let's say like a hard plastic. During this ductile stage, rocks that are undergoing metamorphism have recrystallization events happening. They form new stable minerals that in general tend to be larger than the original. So where do you get this kind of heat that we're talking about here? The first example would be a geothermal gradient. Bury the rocks to a certain amount, they're going to be hot because the deeper you go, the hotter it is. But you don't always need to bury rocks to a depth where the geothermal gradient hits that 200, 300, 400 degrees Celsius. You can get contact metamorphism. This is, for example, say, if a magma chamber near surface, the rocks can hit these high temperatures simply by being near this magma pluton, this magma chamber, or they could hit higher temperatures than they usually would by contact metamorphism. Picture here shows this example, right? Of course, your geothermal gradient scales down, and you get hotter, hotter, hotter the deeper, deeper, deeper you go. So that subducting oceanic lithosphere, for example, melts under these conditions. That being said, if the rock doesn't get dragged down deep enough to actually melt, it gets stuck someplace between the surface and that idealized geothermal gradient, such as that green section that arrow is pointing to there, you can get a level of metamorphism. Likewise, those magma bodies shown in the center, around those, that shallow crustal rock can undergo metamorphism. And shallow burial, if you get deep enough, the gradient can still click in. You can get some shale to slate, as was shown earlier. Contact metamorphism, as I said, flows the exact same way we were talking about. Here we can see a mountain range that has igneous pluton on the bottom, but metamorphic roof rocks on top, because that magma chamber heated up the surrounding rock enough to metamorphize and create whatever that top layer happens to be. I can't tell from this picture, it's pretty far away. As with igneous rocks, when you have temperature, you also tend to have pressure. Pressure is, the deformation component to it, and along with temperature can cause these changes. Leading cause of pressure, of course, would be the overlying sediment. The thicker you are, the deeper you're buried, the more pressure you have, the more deformation you get. Deformation can come in all directions and can close pore space, causing an increase in metamorphism. That being said, not all deformation is uniform. Tectonic activity can cause what we call differential stress, usually a compressional pressure of some force, causing those irregular, bent up strata that we see in example like that folded igneous rock we showed earlier. In reality, all these play an intricate role with each other to produce the rocks that we see. Chemical active fluids can be a small role in this as well, in the same way that fluids played a role in igneous rocks. Water, of course, is very common. And as temperatures increase in the minerals, they expel water. That expelling of water changes the mineralogy. Clays turn to micas, as was shown before. And of course, hot water helps to remove ions from minerals. And then that water flow that's being expelled can enhance the ion movement, changing around, creating new geologic environments. Parent rock. Parent rock is what the rock was before it was metamorphosed. Many metamorphic rocks have the same overall chemical composition as the original parent rocks. For example, sedimentary rock limestone has calcite, and the metamorphic rock marble also contains calcite. It's all dependent on the grade of metamorphism and the environment at which the rock changed that provides you the level of change, the level of metamorphism in the rock. Metamorphic rocks can have various sizes, shapes, and arrangements of the mineral grains and their textures. They can display preferred orientation of minerals if possible, where platy minerals, for example, exhibit parallel and subparallel alignments. We tend to call, this isn't 100% accurate, but a good way to think of foliation is the layering of a metamorphic rock. They're similar at a very basic level. Foliation, is the planar arrangement of grains and structures of the metamorphic rocks. The reason why foliation exists is different from the reason why like layering exists in a shale, but it's basically the way the rock lays on top of each other, the rotation of flat minerals, the recrystallization of the new minerals, and the flattening of spherical grains. Picture shown here about the development of said foliation, the layering, the appeared layering in a rock that's undergone metamorphism. The the granite that we see in part A there has no defined layering or any sort of thought process to its grains, right? However, if we go through metamorphism to B to that gneiss, we can notice that it seems to have lines. It seems to have a preferred direction to the crystals and to the minerals in the rocks. That preferred direction we call foliation, right? It looks like something took that original rock and squeezed it and shoved things up down. This process, as you can imagine, will flatten spherical grains because you're pushing on both sides. You push on the sides of the circle, you're going to get a oblate shape like that, right? The textures have made different, the foliated textures have made different names. Salty cleavage is an example of this. This is where the rock tends to break and form thin slabs. Notice we talked about cleavage before, so here's another example of it. We talked about it with minerals, I believe, in chapter 3, I want to say. That could be a mistake. I believe it's chapter 3, though. Slaty is they look like plates coming off. Platy, slaty, it's all the same thing, except slaty is the foliated term. Schistosity is a interesting texture. It refers essentially to schist. Like a schist is a common metamorphic rock. We talked about that a bit before. And whereas slaty is these large, like table-looking sheets to it, these very thick breakups. Schistosity, or the schist-like texture, refers to the planar layered structure that the mica flakes began to recrystallize into from the large muscovite and biotite crystals they originally had. Visible to unaided eye, this is really something where you just need to hold a schist in your hand and you understand what's going on here and how it differs from, let's say, a platy material. It's kind of hard to show without a picture. I suggest buy yourself a piece of mica schist, take a look at it. It's pretty cool looking. And they're shiny. That's always nice too. Gneissitic textures, as I said, gneiss seems to have this preferred alignment with its crystals. Kind of looks like stripes, right? We call that gneissitic. All these phrases, schistosity refers to schist, gneissitic refers to gneiss, that's intentional. If something looks like it's nice, in a geologic sense, we call it looking like nice. A lot of geology, as I've said many times, very much is not trying to fool you, not trying to be smarter than you. This rock looks like schist. Well, then you call it schisty, right? And then, of course, if it doesn't exhibit any of these major texture qualities, we call it unfoliated because it doesn't have foliation. Quartzite, metamorphized sandstone. Sandstone doesn't have any particular dominant structure to its texture. Quartz does not either. Examples as shown here of many different common metamorphic rocks. Slate with its slaty texture, you get it. Phyllite is somewhere between a slate and a schist with its schisty texture. Gneiss, of course, with its gneissic texture. Then marble, quartzite, hornsfells are examples of unfoliated rocks. Marble may look like it has some predominant strain to it, and it might because of those pressures, but there's a big difference between marble's appeared foliation and gneiss's directed foliation. And then, of course, another interesting component is like those parent rocks, and the two kind of look together. If this rock kind of looks like a sandstone, but it looks like someone beat up the sandstone, well, then you have a quartzite, right? This kind of looks like a granite, but looks like someone beat up the granite, well, then you probably have a gneiss, etc., etc. This looks oh, this looks like limestone, but looks like someone beat it up. Well, you have marble, because that's exactly what happened. These rocks were beat up by temperature and pressure. Let's get into this a bit more with these particular examples. Slate, very fine grain because it comes from shale, which of course is very fine grain, compressed mud, right? Low grade metamorphism results in slate. You don't got to do a lot to mudstone to turn it into slate. It tends to be very soft and somewhat kind of shiny. How can you tell slate from shale? Shale just looks like a piece of mud. Slate looks like someone polished it up a bit. Phyllite is another foliated rock. It's essentially a higher grade of metamorphism than slate. Keep working on that shale, and eventually you get a phyllite. Very glossy, kind of very unique feeling rock. It kind of feels like it needs a wash, but it's clean. Very soft, again, because you just deal with mud here, right? Schist, we talked about that before, comes from various grains of mica. Usually got to do a little bit more pressure to work on mica to turn it into a metamorphic rock. Tends to have schistosity to it, unsurprising there. And very commonly you can find other chunks of high grade minerals such as garnets, or as said before, quartzes, within schist. And that's kind of fun. Again, we can see the layering shown here. I really suggest try to find yourself a piece of mica schist. That holding it in your hand. With all the geology we talk about in this class, it really, truly is best understood by holding it in your hand. I suggest go out there into the woods, stay safe, of course, but look for find these rocks. A lot of these rocks are very common, so you don't need to have a deep, thorough understanding of how to rock hound 101 to find a good variety of geology out in the world. Next time you go out for a walk on a trail, take a look at the ground a bit more than usual. You're going to find a lot of cool stuff down there. Gneiss, we talked about that, of course, before. A banded appearance to it. Looks like there's some sort of thought behind the process. It was on a very high-grade metamorphism, again, from volcanic rocks such as granites. And tends to be a composition of light-colored, feldspar-rich layers and darker ferromagnetic rocks, not exclusively white and black. You can have a variety of this texture because, again, the volcanic rocks can vary greatly in color, so your gneisses likewise can vary greatly in color. Here we have a pink and a black gneiss, right? Because the parent rock for this pink and black gneiss was different chemically than the parent rock for this white and black gneiss. The rocks, the magma that was extruded to produce that initial igneous rock was different, so the metamorphic also have changed. It could also be a difference in grade and surrounding metamorphism. There's 100 different factors to produce each individual rock you see in your day-to-day life, and that's part of the excitement, right? Cross over into our non-foliated rocks. Marble is a recrystallized limestone. It's essentially take a bunch of calcite, because that's what limestone is calcite, right? Take a bunch of calcite, which is very soft, beat it up, you can get yourself some marble. Most of your marble countertops are not actually marble because, as shown here, marble is very reactive to acids. It'll bubble the same way calcite does. See these connections? Taj Mahal, as shown here, is made of marble. Please don't throw any lime juice on it. Right? Quartzite. Quartzite is beat up sandstone. And it's cool about quartzite is you get out a little tiny magnifying glass and you look real close at it, you can still see the grains of sand that were the original sandstone. The difference being those grains seem to be sort of welded together a bit, fused together. Yeah, because that's exactly what happened. Pure quartzite is white. You get colors in quartzite due to oxidation of the original parent rock, right? Iron oxide may produce reddish and pink stains. Quartzite is very hard. Harder, in fact, than sandstone because it's being compressed together. Fluid will not soak into quartzite. It is a strong rock. And again, we can see this one-to-one correlation. We can see, you can picture, if you take the left side close up and you really put a lot of heat and pressure to it, how you can get the right side, right? It looks like a baked version of the left side. This chart's interesting because it does a good job of comparing pressure to temperature and what and where and how these things interact with each other. As your temperature increases laterally along the top, it can affect your pressure increases as it drops there. And the combination of temperature and pressure dictate what is causing the metamorphism. If you have low temperature and low pressure, you probably have some hydrothermal metamorphism, just some hot water flowing through causing the delays. If you really increase the temperature but don't bury it deep, contact metamorphism. And then as you bury it deeper, you get regional, just layers on top of layers metamorphism, all the way up to subduction metamorphism, which is very, very high depth, but not necessarily high temperature always. The two are related, but not as straight of a relationship as, say, regional metamorphism. And all throughout this chart, different rocks will change and alter in different ways to produce the wide kaleidoscope of metamorphism that we have in our world today. Again, showed this image already of the contact metamorphism, as said before. Contact metamorphism is that red splotch up top there. So the magma chamber is obviously very hot. It's melted rock, but it's not super deep, so you don't have a whole lot of confining pressure. The magma chamber is not pushing up on the rock nearly to the same extent as, say, subduction zones. Right? So the shale at the very top of this is metamorphed over to, say, a Hornsfell as it gets closer and closer to the magma chamber. The layer of quartz sandstone below that, because the shale is a lake bed where the sandstone would probably be a beach environment, that gets metamorphized over to the quartzite. And then the limestone, from inorganic or organic means, gets transitioned over to the marble. And the more it transitions is in accordance to how hot it gets, because that's an increased metamorphic grade. Hydrothermal metamorphism here shown most extensively at mid-oceanic ridges, such as the Mid-Atlantic Ridge running through the center of the Atlantic Ocean, uses chemical alteration, less common, but still definitely a thing, caused by hot iron-rich fluids that circulate through the pores in the rocks and can result still, again, metamorphosis. What do you need? Temperature and usually pressure. And if you don't have a lot of pressure, you can still get there with temperature. The chemistry can still be altered even in this exact same way. I said before, burial metamorphism, subduction zone metamorphism. I'm not going to go too deep into this because the names describe what's going on here. You bury something deep, it's going to be affected by the depth of the burial. You subduct something down, it's going to be affected by the subduction event. And then we can get to regional metamorphism. This is essentially all the other components working together on large scales. You've got some continent to continent collision going on down there in B, for example. That collision caused a lot of temperature and pressure to rise on the scale of what is being subducted, thereby creating large amounts of metamorphic rock. Those mountaintops, as shown before, exactly this result. And we can again get this scaling as shown before, depending on where the heat is, where the pressure is, and what is being, that heat and pressure is being applied to. Your high grade metamorphism come from a lot of heat and pressure, whereas your phyllite or your slate comes from less amounts of heat and pressure. And just look at those zoom ins on the grains, and you can see a very close relationship between all these various components. How the semi-parallel yet separate slate that's sort of uniform in color can kind of be warped and bent by the heat and the pressure, so much so that it starts to break and separate like the schist, and then finally is completely broken and separated like with the gneiss. Within the metamorphic rocks we talked about before, we can have index minerals, such as, again, the garnet with the schist, that are good indicators of the metamorphic environment, because, again, rocks are not uniform. Rocks are not this big clump of only this one particular mineral, for example. Rocks tend to be a collection of many different minerals, and since different minerals metamorphize at different temperature and pressure grades, if you have this mixture and it doesn't get quite to the level of metamorphism to, say, affect a garnet, which is, I think, just melting. I don't think garnet metamorphizes, so I could be wrong. I apologize if I am. then that tells you exactly how hard. Oh, there you go. That tells you how hard something was metamorphized. So garnet is actually an intermediate grade. Wow, I was way off. Poor me. But yeah, so garnet is, if you see a garnet, you know that you didn't get to high grade because garnet's not gonna exist at that level. Whereas if you get, let's say, if you find chlorite, well, then you had very low grade metamorphism because chlorite's not, I was thinking quartz when I said garnet. Quartz isn't going to change in this level. Quartz is very strong. If you have chlorite in your phyllite, that says you have a very low grade of metamorphism because if you get to intermediate grades of temperatures and pressures, chlorite's going to be tumbled all up in your schist. Right? That, in very quick synopsis, is metamorphic materials. I hope you enjoy the conversation. As with always, this is a very complicated subject. I'm doing an introductory level conversation in it. Please look up this information if you find it enlightening and learn more about it. There is a whole wide, exciting world of geology out there. Metamorphism is one of those parts. Make sure comment down below if you have any questions, and stay safe.